back, everybody. We're going to continue our conversation on Monte Carlo techniques. And then when we get through that, I'd like to give you a brief introduction to Markov chain Monte Carlo. What I really want to make sure is we understand why we're doing all of this. So, can anybody articulate our pathway, why we're studying Markov or Monte Carlo in the first place, and why we need to sample from distributions? One heat. No idea? Painful.
I would say it's computationally easier on the computer. And when you new age, you have all this computer stuff, you want to be able to sample efficiently and do things faster, right?
Oh, I see. Okay. So we're going to jump the gun to efficiency. Let me just make a point. I don't care about efficiency up front, And so I optimize late. I once thought I would study like programming optimization until I realized people have done this already. And a lot of times you're working on optimizing the programming languages, what they do, and how to write things the most efficient ways. I decided a long time ago, just write it, prototype it, and then you have something to improve. I talked to an optimizer, somebody that was an expert in this, and said, you never optimize your code when you first write it. You write it later. You optimize it later. So we'll be talking about the efficiency of everything soon enough. But let's just take a step back. Why are we even sampling from distributions? Sean?
Finding an analytic form of the posterior can be really, really hard.
Okay, but what if I'm able to write down an analytic form of the posterior up to proportionality? So say I can write this down. So Bayesians do this all the time. So posterior distribution is proportional to the likelihood theta given x times the prior. So while sampling techniques can be applied to any distribution, in learning about that distribution we can do through sampling, Bayesians have particular distributions that they work with. So if I can write that down, bam, maybe I can, maybe I can't normalize it, but I'm going to say I don't care because I just care about the shape. The relative posteriors to things, and you knowing this is enough to do all of your inferences. If you can normalize it or not normalize it, it's never made a difference to me, except for like point process models where the normalizing constant is a constant with respect to the sampling distribution, but it's not with the likelihood. Be careful with that. So sometimes your likelihoods are not, the constants are not the same constants because likelihoods are over the parameter space. So what people call constants are not constants. I usually call them integrating factors, just to make sure we're talking about the same thing. Sampling distribution for a normal distribution, e to the minus quadratic form, is the kernel of the sampling distribution. 1 over sigma sits out in front of it. So that 1 over sigma is a constant for the sampling distribution, but it's certainly not a constant for the likelihood. And if you forget to write that term down when you're doing variance analyses, you've just messed up. So be careful what we call constants in all of this. But if I can write that down and I have all of the terms in my likelihood and my prior, and I have good reasons to pick my priors, we're starting to develop a toolbox of good reasons. Why we like certain priors, I tell you, as a location parameter, you probably make a snap judgment. Flat prior, sounds good. Scale parameter, 1 over that parameter. I don't care how you're thinking of it, precision, standard deviation, variance, 1 over that thing would be a good choice. Anybody want to add to the conversation? Why are we doing what we're doing? If you don't think that way in your classes, why are we even doing this? I'm not sure what you're doing.
I agree with Sean, but
okay, cool. We've got some backup. Anybody agree that there's more to the conversation? Do I have any backup?
If we get samples, then we don't have to integrate.
Yeah, integrating is hard. So anything to do with integrals is really hard. Understanding the area under the curves is necessary to compute almost anything. So just because you can write down that analytically does not mean you can write down the integral analytically. You ever take a calculus class? So there's some doozies in there. There's doozies to the point where you can't even write down the integral analytically. So the integrating analytically is kind of the key. Sometimes that's really hard.
And is another reason why we want to be able to integrate because we want to be able to find confidence intervals? Sort of.
Confidence intervals. Oh, just put me out of my misery right now.
Because I choose the wrong.
Yeah.
Like,
Credible intervals. But credible intervals could be confidence. They could cover. There's a different series of lectures on that. Credible intervals could be confidence intervals, but Bayesian intervals are credible intervals. So at least let's get the branding right on this thing. We went through a lot of work to get some name brands on this stuff. Let's at least use them and not this generic term that we learned before. So some credible intervals are confidence intervals. Credible intervals are belief statements. They tell you where the mass of the distribution is. Shortest ones might be preferable, and in some cases credible intervals could cover, and they have confidence properties. Probably better than your asymptotic buddies that say they're frequentist. The Bayesian could be optimal in all kinds of different ways. But basically, if I wanted to form an interval, I need to measure areas. So of things, if I want to compute expectations, I need to integrate. If I need to compute variances, I need to integrate. So all of those problems, if I want to come up with posterior predictive distributions, Monte Carlo could be helpful for that. So what am I doing in a posterior predictive? I'm integrating out the parameter space by sampling from the posterior and subsequently sampling from the sampling distribution, taking that sample from the posterior and plugging it into the sampling distribution and resampling out of the sampling distribution is integrating out that parameter. So it all comes down to integrations. So we're trying to avoid doing everything by hand. And in most cases, you can't. So that was basically the non-Bayesian argument, the way I see it, back from the 60s. You argue philosophy, but you can't do what you're claiming you should do. So then you approximate away. So are the approximations good? The old approximations, probably not as good as the new approximations using our new computer horsepower by collecting samples. So this is the way I feel about it. If I can sample from a distribution, I can learn anything I want about that distribution. You give me the ability to do that efficiently, and I can do it fast for you. So, but at the same time, depends on the context of the problem. If it's a one-off sort of problem, then I might want a very refined answer, and I'll spend a lot of time sampling from it and building my best model. If I'm just trying to forecast fast and come up with something approximate, some not nonsensical answer real quickly, I might come up with something where I don't have to integrate. I might optimize real quickly, do something else. But sampling gives us the ability to learn from any distribution. So some distributions are easier to sample from than others. So we are in the middle of studying a couple algorithms for plain MC. So I usually like to call this vanilla MC. Vanilla is my favorite flavor, so no disdain to being plain. So Markov chain, we've got a bunch of different algorithms that we kind of looked at. I'm not going to quiz you thoroughly on these, but I want you to at least understand why we're sampling in the first place. So what sort of MC algorithms have we studied so far? Just plain Monte Carlo, not the Markov chain appendment. So this is Monte Carlo. Gives us the ability to basically understand anything we want from a distribution so long as we can write it up to proportionality. And this will be a common thing in Markov chain algorithms that a lot of times you don't need to know what the integrating constants are. We'll see that in a second when we write down our examples. So this part is Markov chain, and we'll get there later. So this is a special brand of Monte Carlo algorithms, and the math that underlines these algorithms is inherently different. So if you know all about Markov chain, stochastic processes, you use that sort of math. So for just plain Jane Monte Carlo, we have different sets of theories to govern how good those approximations are. Somebody just tell me what the underlying theory of plain Jane Monte Carlo is. I told you last time. Pink.
Monte Carlo is a computational algorithm by doing sampling.
Yeah, that's true. It's a sampling algorithm. Plus 1. So what's plus 10 look like?
I was gonna say, it's like, it gives you like a random answer in a fixed amount of time.
Yeah.
And the more samples you get, the better or closer answer you get.
So what's the mathematical theory that underlines a lot of those concepts? Law of large numbers, even better than that, CLT, central limit theorem. So we're usually looking at sums to approximate our integrals. So we can directly apply the CLT. So all that stuff from Stat 101, now handy, and you get to control what the number of samples are because you write the for loop. So that's kind of nice. If I'm going to be asymptotic in any of my approximations or frequentist, I want to control the frequency. That's why I think frequentist paradigms work really well in like factory setups, where you're able to reproduce things over and over and over again and really monitor the frequency. Make sure that your paradigm adheres to the problem. So biology, we only ran it once, you know. I want to know stuff about your genome. If I were going to do a frequentist paradigm, I'd need a time machine in a multiverse. So to have that fit for me. So anyway, that might not be the best thing in the world, but I do use frequentist paradigms when I understand Monte Carlo algorithms. So give me a Monte Carlo algorithm that we studied last time.
Accept, reject.
Accept, reject. We are right in the middle of this one. We need to finish this. Accept, reject. Does anybody know any other names for this type of sampling procedure? Sometimes this is called envelope sampling. So think of G as an envelope that houses F, what we want to sample from. And so I can stick F right in that envelope of G, i.e. G needs to tail dominate and cover a lot of times your proposal. And that's certainly true in the accept-reject algorithm. So sometimes you'll hear this called envelope sampling. When I learned it in 3rd grade, it might have been 7th grade, that's what they called it. Throw darts, you know? Make the board that you're throwing at bigger than the target, and then count the number of things in the target compared to the board. Just make sure you can always hit the board. So that sort of thing. Any other algorithms? I think we studied a bunch. We looked at Monte Carlo integration. We looked at an analog of this, an immediate extension. What was that called? Importance sampling. Where we studied that the importance weights were Fx over G of x, where x is my random variable. So these are my importance weights. We motivated this through Monte Carlo integration. That video will hit the YouTube page soon if you haven't had a chance to rewind. I noticed that I didn't post it on Friday. It's posting right now. The importance weights. If I take all the points that I have for each one of the points that I sampled out of G, and I re-weight them by this, so I take weights proportional to those weights, and I have its accompanying point with it, and I take all of those weights and I normalize them, and then I sample those points with those weights, it'll actually give me samples from F and not from G. So that's kind of cool. So F might look like that, our target. And G looks like something that's easier to play around with, but it's fatter tails. So G is my proposal. I drew this a little bit not proportional just because I want to show that G is supposed to cover F. My drawing's a little bit messed up. Let's unnormalize G. But we know we're supposed to lift that up by a factor, but I'll just say, let's say we've got a G right here. So, and it's easier to sample from, I know how to sample from it. So what are these weights representing? They're the difference in a ratio sense of these areas right here. And so it's down weighting and up weighting depending on if G had lower weight or higher weight than F. This is the correction factor. I'll show you that in a moment. So important sampling. What other algorithms have we studied?
Box-Mueller.
Box-Mueller, we at least described it. Box-Mueller, this is for normals. And I will say there's Box-Mueller-esque algorithm for gammas and chi-squareds as well. So we've also studied a little bit of how you sample from T's if you know how to sample from normals and gammas. You can use mixture representations to do that. So that's kind of cool, and we're going to exploit all of that. Markov chain Monte Carlo has a Markov chain aspect, and I want to tell you a little bit about Markov chains before we delve into it. Let's at least finish this right here and show that the accept-reject algorithm works well. Just real quickly, what do I need to do this algorithm? So there's certain things I need to do up front to be able to employ this algorithm. What is it?
We need to know some factor that we can multiply G by such that it doesn't get overtaken by F.
So it dominates. So it does the overtaking. So it always overtakes. Yeah, so I need a factor M that I can raise this up. I can actually raise it higher, but that affects my efficiency of the algorithm. So you would want to try to make this efficient by optimizing this M. I need a proposal that tail dominates. Its tails are heavier than F. So I need this ratio right here, a scaled version of it, always to be bounded by 1. So I need to multiply G by M so that it's always over the top of F. And that's just what we need. So that kind of makes sense. If G is not going to put samples as often in the tails as F has, you're going to have a hard time learning about those tails. So you want those samples to go out to the tails so that you can learn about the tails. If an algorithm has a hard time proposing into parts of the space, you're going to have a hard time learning about that part of the space. That kind of just makes sense. So you might say, why not just take like a constant function and drop it over the top, but in an infinite continuum, you can't do that. But in a bounded sense, if everything was bounded, that might be what you want to do, but you'll make your algorithm probably as inefficient as possible by doing that. So, a couple assumptions in here. Let me just show you another one, just before we finish up accept reject. This one we've at least alluded to. I've heard it about 5 or 6 times be brought up in this class, the inverse CDF method. Inverse CDF sampling looks like this. If I want to collect samples, so here's our goal. This will always be our kind of naive goal. I want to get X's from F, some density function. You could turn this into a discrete function, a mass function, but I always like to just kind of generalize out of the density function. So all this stuff that I always write down with density functions immediately applies to mass functions. Same thing will work. So xi from f, I'll just write in a dummy argument right there. And so how does the inverse CDF method works? First, you compute the CDF. F of x dx, and I'll write minus infinity off to x, just to give us some notation. This x, and that x are not the same x's. This x is that x, this x is that x. So hopefully you're on to the game. Same mistake that my calculus teacher used to say, stop writing it that way. And I'm like, I'm gonna not, because everybody else in the universe does it. And so, but you get my point. So that's the CDF. Then I can find the inverse CDF. Let me ask you a question. Are CDFs always invertible? Yes. So just as long as you make a rule for if you have flat ridges in your CDF, that means they have no mass in certain parts, you pick a point from that interval. You can map it arbitrarily to any point, you know, but usually people take them to be the endpoints. So of those things. So if your PDF comes down, has 0 mass and a point, when you're integrating across that, your CDF will be climbing until it hits that flat region, and then it'll just flatten out. So you need to just make a convention of when you invert that flat region, because that part's not necessarily 1-to-1, you just pick one of the endpoints. So, and then this always exists. So yeah, in a easy generalization, I don't even need the generalized inverse or pseudo inverse or anything like that. I just need a common sense rule. So give me one point in that thing, and usually people take it to be the left end point. So makes sense. If it's in a continuum and you take it to be the right end point, it didn't make any difference. So mathematically, it's all the same measure. So this always exists. So F inverse, so the algorithm looks like this. If I take U from a uniform, zero, 1, and I take F inverse U, and I set that equal to some value, I'll be real specific. For each U, I get an xi. This thing right here is distributed according to F. So what did I do? I took the inverse CDF, that's a formula. I plugged in a uniform random value, and I transformed that random value. So this transform is always giving me samples according to our original density. So later on when we study p-values, you'll understand that p-values are uniformly distributed under the null hypothesis for exactly the same reason this happens. It's exactly the same mathematical proof, the same equation, same everything. Let's just write it down real quick. So just a proof of this statement is, I want to know what this thing is right here. Let me just give it another random variable name. I'll just call it x is equal to F inverse U, where this is my space of uniforms. This is my space of x's. That's my random variable. So that's the space I'm mapping, and this is the conversation we had and belabored that I can map points in the space or I can map the whole space. It's a concept. So proof of this right here, I want to know what this thing is. So the probability of x is going to be less than or equal to some value. I'll just arbitrarily call it x. So this is the probability of F inverse U less than x. Right there, I've just replaced its name, showed how I compute this thing. I can rewrite this again. U less than or equal to Fx right here. And what's the probability that a uniform is less than whatever number this is? So this is some number. It lives in a particular range. I always like to check these things as a mental sanity check. Where does U live? It lives between 0 and 1. Where does cap F live? Between 0 and 1. It's a cumulative function, and we arbitrarily like the number 1 a little bit more than other numbers. So we've just arbitrarily said that when we add up CDFs, they add up to 1. So it would have been nice if they made it like 17.2, but they didn't do that. They stuck with 1. We can remember it easily. So what's the probability that a uniform is less than cap F? It's cap F. F of X. Right here. So let me say it a different way. What's the probability that a uniform random number would be less than 0.75? 0.75. That's how much mass is to the left of it. What's the probability that a random uniform number is going to be less than 0.05? It's 0.05. That is the part you'll probably use in the p-value proof later on. We'll be thinking of that special number, but they could have been picked any which way. So this works. That's a complete proof. Here, I'll make myself feel good. Remember, I used to feel like I did something when I made that little box before. Or you could do this. People like that one. Or how about being a real jerk? QED. What does it stand for? Why do people write it? It's just part of the culture. It feels like proof. Okay, so we're triple proofed on that one. That was pretty easy to do. Inverse CDF works. When does it work? When I can find the CDF and when I can invert it analytically. If I can't do those two things, not so easy. So for a normal, you can't write down the CDF, let alone invert it. You can't write it down in closed form. You can only approximate it. So a lot of algorithms, this would be nice to do, but you can only do it in special cases. Box-Mueller works in special cases, so accept, reject. There's some caveats there. I need a constant to multiply everything by to lift G above F. So that can be hard. In high-dimensional spaces, you can't really use this algorithm. I would agree you can use the concept of this algorithm to build something, but there's no cumulative in high dimension. So what makes high-dimensional space so much more difficult than one-dimensional space? Let me just ask that as a general question. What makes high D space so much harder? There's probably two good reasons.
Can't visualize.
Okay, can't visualize it. That's true. So I mean, I'm good up to 2D with a little bit of color, right? You can give me 3D. So we're limited in our visualization of everything. That's true.
There's no ordering of the space.
There's no ordering in the space. So I think that's super important. I think that we instantly indoctrinate people to think about means, medians, modes, ordering of spaces, what's best, what's not best, here's a ranking. We should stop, you know? So, because as soon as you take into account 2 dimensions, it's not clear. You know, anything higher than 1-dimensional space, you can't naturally order, you have to build arbitrary rules to everything. And then it's also mostly empty, so I would say. So most of it is empty space, and that makes it hard to work with, and that's why quadrature usually is defeated by Monte Carlo techniques. So let's just look at accept, reject real quick. Write down a proof for this one. So the AR algorithm looks like this. So I'm going to sample a U, and I'll be specific. This runs in a for loop. For every xi that you generate, you've generated a new uniform. If you're always using the same uniform in your algorithm, you've made a huge mistake. So uniform is going to come from uniform. And then we do this. We take xi. We're going to have a condition. I'm actually going to check some conditions. So I'm going to first accept, or I'm going to propose x star. I'm going to do it from its function g of x. This has a special property. It tail dominates f. So I know how to sample from that, I know how to do it. If you pick a distribution that looks a lot like F and you don't know how to sample from it either, it didn't help you. So you need to know how to sample from this. So you might use one of these other algorithms to sample from something that's easier to sample from and heavy-tailed. Good candidate is usually something like a Cauchy, but that might be too diffused for you. But those are heavier tails than all your stuff in the exponential family. So that's kind of nice. So X star from G, then we're going to check a condition. If Fx star over Gx star times M, and this M is picked, so this thing is less than 1. So we pick this M in advance. What that means is that we're able to raise this G function over the top of this thing. And that's what it looks like, and it always stays above. If the tails come down faster in G than F, they'll eventually duck the tails of F. And so maybe way out where, and that's going to make this ratio really unstable. So it's going to have a lot of variability in that ratio, and the variance is actually going to be infinite when you do that. So you probably need to be very careful about this. Finding an M such that this is true in one-dimensional space is exceedingly easy because of the ordering of the space. Use your favorite, optimization tool in 1D and just march through this and check for the maximal difference. If I can write down F and G, I can do this. So again, the presumption is I can write down what F and G is, but that's different from sampling. So just because you can write down a formula, it doesn't mean you know anything. So if you can sample from the function and measure all the areas in different places, now you can tell me all about that function. So I'm going to check this condition. If U is less than that, and uniform 0, 1, guaranteed to be bounded by this, so I'm just going to erase that thing right there. We know how to pick M, or at least we have an idea on how to pick M. If this is true, then xi equal to x star is coming from F. This is a big if. What happens if this doesn't occur? What do? Do it again. Do it again. Keep doing it. Generate a new uniform and a new x star, brand new ones, and check it again. So you're going to run this into a loop until this is satisfied. All the other ones you just throw away. You don't get anything for it. So you could say to your advisor, yeah, but I sampled 1 billion of them and it's taken me all day. I even did it by hand. Don't I get any credit? And they say no. No credit until you give me some samples. So accept reject is well-named algorithm. You either accept it or you reject it, and when you reject it, you throw it away. That's going to be different in MCMC. You don't throw things away. You keep them. So just keep that in mind. So we already studied how often this happens. This happens with probability. We wrote this down last time. Can somebody help me to remember what this number is?
1 over n.
1 over n. So this is the acceptance rate. Now keep in mind, I like to think about these things a little bit. If F was G, then the perfect G that I could pick is F, if I could do it. If I ran this algorithm with G being F, I could pick M to be 1 because that would always be bounded by 1. They're the exact same functions. It always is 1. And so all I would be doing is evaluating this for no reason and generating a uniform for no reason. So you would already know that it's accepted. But the acceptance rate would be 1, and so that's a good sanity check that our math makes some sense. How did we work this out? Let me just remind us, and we'll conclude the proof for accept reject. So this thing was just the double integral of the joint distribution. The joint distribution is g of x times 1. So our joint proposal, these two things. This has PDF G, this has PDF 1. So oftentimes I don't write that down, but that's the PDF for you. Now I'm going to end up integrating du dx right here. Where am I going to integrate u from? I need to respect my bounds, so not between 0 and 1. I guess I could write this out in terms of finagling with the bounds of g or x, but I would rather finagle the bounds of u because it's already written down for us. So 0 to f of x over m g of x. Same notational abuses as always. This bothers you. You can change this to any dummy variable you would like. And then I'm going to integrate x over its entire area. So a lot of times I'm just writing down infinity, negative infinity to infinity. But just to be really clear about this, to make it a little bit more general, I'll just write over the whole region of x. So I'm going to integrate the whole thing. There's no x's in that equation. And we ended up getting, this thing is the integral omega x. I'm going to do the integral with respect to u. That's pretty easy. So that's just f of x, g of x times m. And then I have this g of x over here. I'll stop writing down the times 1. This is going to be over x. Right here, these two things cancel. When I integrate the density of f of x, that integrates to 1 because I'm integrating over the whole space. So that's just 1 over n. So that's how often we accept. Now let's just prove real quickly that our algorithm is doing the right thing. So let's just write this down. To do everything, what we need to do is we have to understand the probability distribution of whatever this transformed random variable is. So let's just look at the joint. So the joint of x and acceptance. So I need to consider two things: how I generated x and that we did accept in the first place. What does acceptance mean? It means this happened. So that's that. We already know the probability of that. So what we're going to do is we're going to take the probability of the joint and divide it by the probability of the margin. The marginal probability of its acceptance, that's going to be 1 over m. We just figured it out. So this is just this integral. Integrate, same thing, just transforming my joint density, writing it out as a probability statement, du dx. So now I'm just going to write this 0 to f of x over m g of x. So same thing as before. So that's just our acceptance criterion. And now I'm going to integrate. I'll write it out like this: minus infinity off to x. So I'm adding up to the x thing. So I have a cumulative on that. So that's like acting like this variable right here. I'll point out this can be done in high dimensional space, so the notation I'm using doesn't really coincide with that. But all of this is still true, and I can butter up my notation by being explicit about the region I'm integrating. This thing right here, we've already done this integral, except for the outer integral right here. So before, when I integrated over f of x, I integrated over the whole space, and now I'm going to integrate up to a point. So that's a little bit different. So using the same rationale for doing our integral, it's just that thing. This didn't integrate to 1. If I took x and blew it out to infinity, then that would go to 1. So that's this. This is the joint. So the probability of the x's conditional on acceptance. I'll write down using the same notation before conditional on acceptance We already know what that means. That means that this happened right here. So what I'm going to do to come up with this thing is this is going to be f of x divided by m divided by the marginal probability of acceptance. So I take the joint, which is that. I divide by the margin for acceptance. And that's just 1 over m that we had before. So if I want a conditional probability, I take the joint divided by the margin. These m's cancel, and this thing is f of x. So this provides me samples from this probability distribution. So the samples are distributed according to the coinciding density with cap f. And we know what cap f is, how we got it. That's little f. So this algorithm works too. Caveats to doing this algorithm: you've got a good proposal, but you can also figure out this m. And in high-D space, not so easy. I like this algorithm though, because it kind of tells me everything I need to think about in Monte Carlo. So I want to just point out this ratio appears again, f over g, so the importance weights are in this algorithm. So that importance weight, that ratio of everything, is exceedingly important. So if I propose something from a different distribution, what's my correction factor on getting it reweighted properly? Same weights that we saw before. That's cool. I like that. Make sure there isn't one more thing I want to say about this. Okay, I think that's okay right now. Let's jump into Markov chain Monte Carlo. So all that, I suppose I can do all of these things. Sometimes you can't do them. And so sometimes you might want an algorithm that is a little bit more flexible. You've written down some great model. For your posterior distribution, it's likelihood times prior. You can at least write that down analytically. You want to gain samples. It lives in a high-D space, although my examples are going to be pretty low-D for at least my first examples. And this is prohibitive. You don't know how exactly to find that m. So you might want a general purpose algorithm that always works for you. Of course, there's going to be a caveat. You've got some good g, and we'll talk about good g's in the next lecture. So strategies for devising these g's. Nice thing is you can use some dependence in your search algorithm. So keep in mind, every time you throw out a g, in this algorithm, you're grabbing it independently. So one thing is you might say, okay, I've got some sample from F, and I've collected a few good samples from F maybe, and they live in a certain vicinity. I should be able to use that information to say there's some mass over here. So let's not just propose independently, but let's use the information that we found some good stuff to help us search. So any algorithm that's searching a space, Markov chain algorithms, optimization algorithms need to do two things very well. Exploit what you already know. So you found samples in some high mass part of the space. That's good. And also be able to jump out of there every once in a while. So some of the algorithms I'm going to tell you about don't have both abilities, but if I had a unimodal problem, I wouldn't need to jump too far. So we're going to be studying first unimodal problems, and maybe later on I'll tell you about multimodal problems. Okay, let's just have a glance at what we'll kick off with next time. Again, this is meant to be fast. I don't think I'll test you too much on Markov chain algorithms, but I'd like you to understand the ideas behind them. The only way to really understand any of this stuff is to code it up and see it fail. You know, and understand where are the limitations, what's hard, because it's easy to sit there and For me to say something is hard, but to experience it's hard is a whole different thing. So I would recommend code these things up on problems, see what works, what doesn't work. If you're using a Markov chain Monte Carlo algorithm to sample from a normal, that's probably not a great idea because we have a much more efficient algorithm out there. Okay. So Markov chain Monte Carlo. So some preliminaries. We want to sample from a distribution. This is unfortunate, I called it P. Think of the P as F. It's our target, that's our goal, we want to sample from it. So it lives in some space, we'll call it X. No, I will not give you these slides either. So it takes me time to make things like these. So just a presentation. So P looks like that. It's supposed to be complicated. I would agree I was a little sloppy in making this picture. Somebody pointed out they took a ruler and said that's not a function. So it's supposed to be a function. Sorry, it's a weird angle. It's an optical effect. That's a one-dimensional line representing a two-dimensional surface. I'm just not savvy enough to draw that thing. So it's just an optical effect, we'll say. So it's sufficiently complicated, we don't know how to sample from it. We know how to sample from another distribution and maybe walk around the space and try to explore it. So maybe I can come up with some distribution that walks around the space and explores it. If you're thinking Gaussian random walk, Brownian motion, anything like that, you're on the right track. So I'm going to just random walk around the space. What I'm going to do, at least conceptually, is just pick some sort of a circle or an ellipse around me and grab points in that ellipse, and maybe I could use a Gaussian distribution to do it. I'll be more specific next time when we get to the chalkboard and write down what the algorithms look like. So what I'm going to do is I'm just going to grab some point in the space. So I'm starting in some high mass part of the space, and I just have some point, and I'm going to start there, and then I'm going to start random walking around the space. You could use an independent proposal, but it kind of defeats some of the purpose of what you might do. There are cases where you'd want to do it, but I'm imagining my proposal is taking some walk around the space. So it's kind of just searching for me and checking things out, just like any search algorithm does. It kind of just moves around the space and tracks what's high density, low density stuff. So I'm just going to be spending time walking around the space. This is at least what the outcome of a Markov chain Monte Carlo algorithm looks like, is it takes some time circulating around the space, and the amount of time it spends in the space eventually will be proportional to the area under the curve. That is sampling. So I run the algorithm for some amount of time, and it's kind of bouncing around, and it says, whoa, I found another mode, check that out. And it's learning about that mode. After a while, I can take these samples and I can plot a histogram over the top. Now you can see from my picture, I haven't explored this part of the space yet, and I haven't learned anything, and my histogram is a rather coarse approximation. If I keep running this idea, and I'll put math to the idea and tell you the correct way to walk around the space, next time, eventually this histogram will get really refined and start to estimate this density. And eventually it should make its way over here as well. If I have a proposal that never proposed anything over in this part of the space, I'd never learn about it. So our proposal is going to have the same sort of requirements, that it's got to be able to place mass anywhere there's mass on F. So it needs to have more support than F at least. It can't have less support. So you might ask, does it need to tail dominate? And the answer is no. It doesn't have to, but the algorithms do work better if you do have tail domination. So it's not a strict requirement. So what I want to tell you about next time is the actual Metropolis Hastings algorithm. I'll tell you how this works. I'll introduce the proposal. Instead of G, we'll call it Q. So my F and G are now P and Qs in this presentation. And so there's this simple set of rules that we go through to evaluate if we want to accept our samples. The one thing I want to kind of point out is that you're going to accept samples with some probability. We'll discuss this probability and why it's a good idea. We won't go into a full-blown proof this next time, but I'll at least give you the ideas behind it. But if you don't accept, you stay in the same location. That means you store the sample. So if you're walking around the space, and you evaluate some probability as to whether or not you make the jump, and you don't make the jump, you don't throw that sample away. You store its frequency. And you say, the last sample I saw is my new sample, and the sample before that is still stored in your collection. And what it's telling you is that that's a high probability space. You probably don't want to move away from it so fast. Sakshar?
Is this algorithm for any distribution?
Yes. So if G is formulated with minimal assumptions, of course we need G to basically be able to move around the space, check out the whole space, not do it with any like predetermined patterns, and it needs to be able to go anywhere in the space eventually, meaning that it can also come back eventually as well. So we're going to have G set up so that it's not divergent and doesn't just drift anywhere, but the ideas are pretty conceptual, that if G can circulate around the space randomly and come back eventually, then this is a general algorithm and it'll work for anything. So that's kind of the cool part. So there's different strategies for picking your proposal, and I'll spend a little bit of time next time talking about various strategies. And then we'll study an easy one, the most common one, and that's what your homework will be based off of. We won't have a review session this Thursday, we won't have class this Friday, but next Thursday, in 2 weeks, we'll have a review session. We'll have all of class next week as well, so just a reminder. That's it for now, you guys. Thanks so much.